Yeah, so the notebook that we built together last time, we kind of left off in a rush. So remember this notebook. I'm going to go ahead and run it again. And we had, hold on. Yep, so we had solved for the temperature, and then we plotted the temperature. Okay, sorry, so we start over here. We had 100 points, okay? And then we plotted the temperature. On the y-axis is the temperature value in Kelvin, and on the x-axis is the location along the rod. Overwrite, okay? So let me dim the lights a little bit. So I think this projector has problem. It's quite dim, so we'll see if they can come and fix it. So now note the power of what we've built so far is that governing equation that we've had, we have a lot of knobs that we can play around with. We can change the heat transfer coefficient, K. Remember, we're doing d2t by dx squared minus s of x over k. And I said K was called the heat transfer coefficient, and it tells us how fast heat dissipates along the rod. Okay? So the higher the K, we expect more of a uniform temperature along the rod, right? And the lower the K, we expect more of a non-uniform temperature because heat is going to be concentrated where the heating source is. Okay? So let's go ahead and play with that a little bit. So I'm going to make the temperatures now, both of them 300. Okay, we're going to keep K at 10 to the minus 3 just to see what the answer looks like. Solve it again, and indeed, you see, it starts at 300 on the left, goes up to where the heating source is, to 335, and then goes down. Now, these two endpoints are important when you're looking and checking if your solution sort of solves the problem you're dealing with. We at least satisfy the boundary conditions. Right? At the endpoints, our boundary conditions were 300 kelvins, right? And indeed, our solution returns 300 Kelvin for this point, 300 Kelvin for that point. Okay? The heating source, keeping it fixed, let's see now the effect of increasing the heat conduction coefficient. Okay? So now remember this scale over here from 300 to 335. I'm going to go ahead and actually fix the y limit. And you can do that with plt dot ylim. And I'm going to do from 300 to 340. Okay? So that fixes the y-axis. So now any change in temperature, okay, we're going to do it based on, we're going to see the change, and we're going to keep that fixed. So that's our relative reference. Okay? That's our reference. So now if I increase K, my claim is that the temperature is going to dissipate along the rod much faster because there's faster heat transfer going on. So let's reduce it by 1 order of magnitude. Go to 10 to the minus 2. Solve. Oh, look at that. Immediately dropped from 335 to barely 305. So what's happening here, yes, you are heating the rod, but from the perspective of the heating source, the endpoints are cooling it, right? Because they're at a lower temperature than the heating source. So heat is coming in, but it's quickly escaping. Ends at 300 degrees. So you see this kind of smaller temperature profile. And this effect is significant, okay? It's simple. We went from 10 to the minus 3 to 10 to the minus 2 in thermal conductivity, and this is what happened. In other words, this rod is not a good insulator. For an insulator, you want a very low thermal conductivity, so heat doesn't escape as quickly, right? So let's do one more, 10 to the minus 1, and solve this. Look at that. It's pretty much going to be uniform along the entire rod. Okay? What happens now if my temperature is at 350? Now, this course is not about heat transfer, okay? But I'm trying to use just basic common sense to reason with a numerical solution you have about a problem. As you develop your physics knowledge about engineering systems, you'll be able to assess your solution better based on the physics that you're dealing with. But this physics is fairly simple, right? Heat is coming in, heat is escaping. We can kind of negotiate with that a little bit, okay? So now when the temperature is at 350, okay, we're going to see a little change, okay? It's going to go up to 350 actually, exactly as we expect. It's not exactly a straight line, but it's almost near a straight line. Okay, it's almost near a straight line. Okay. Now you can take k to the other limit. So we're going to go back to 300 over here and go back to 10 to the minus 4 for k. Actually, 10 to the minus 3, that was our. So 10 to the minus 3, okay, the temperature is here. I'm going to drop this limit over here. So it went up to 335, okay? Now, if I reduce k, it means the material in the rod is not allowing heat to move along the rod. So if I'm heating it at one spot, that heat is going to get concentrated and concentrated and concentrated, right? And therefore, we expect the temperature to keep going up and up and up as we reduce k, the thermal conductivity. So let's see that happens. So now k 10 to the minus 3. Let's go to 10 to the minus 4. Solve and run. Look at that. It went up to 650. Still the same profile, same shape, but the temperature at that heating source is spiking. Why? Because the rod is not allowing heat to dissipate or escape through the endpoints. Okay? Now you keep pushing k lower, and this model actually becomes unphysical. Again, 10 to the minus 5. Look at that. You get to almost 3600 Kelvin. That becomes unrealistic for this model because in practice, we have mechanisms to kind of dampen that temperature. The temperature cannot go higher than the flame temperature. Anyway, but this is what these methods allow you to do. Look at parameter changes, change the parameter. You don't need to go to a lab and run experiments and wait for hours and experiments breaking. All you have to deal with here is your code breaking. But if it's working, a model, a mathematical model is one of the most amazing accomplishments that science and math and engineering has given us, right? With the change of a number, you can study an entire material. Now, you can go ahead and play with these numbers. You can make the temperatures higher than what the heating source is. So then the heating source would be essentially like almost cooling it maybe, right? And so you can move the heating source location. Here's another example. So let's go back to 10 to the minus 3. I'm going to go back to the source, and I'm going to put it at 1/3. Remember, we put the source at 2/3 from the left. We're going to put it now at 1/3 from the left. So now our spike is going to be on the left end. You can add 2 sources to it. It will just all work beautifully, okay? Okay, so now the source is at 1/3, and you run it. You see that spike over here, okay? So I can add one more source. So I'm going to add another source here. One of them, I'm going to place it at 1/3. So I'm going to place the first source at 1/3, and the second source at 2/3. See what I did? I just added 2 Gaussians, right? So this is my source now. Got heating at 1/3, heating at 2/3. So now we're going to see 2 spikes in the temperature profile. Well, didn't spike because it merged them together. Okay, they were so close to each other. Now we can make the standard deviation smaller to make them sharper if you want. So we can go 0.01. Let's see that. Look at that. It just merged them. Well, not what I expected, right? But I trust this now. I trust this, what this is telling me. Okay? All right. One more little trick that you can do to visualize this is instead of having just a 1D plot like this one, want to create a color map. Okay? A color map. You don't have to do that, but it's a little trick that I'd like to show in this class. There's a function in matplotlib called imshow or image show. It takes a matrix and converts the numbers in the matrix to a color, okay, to an RGB color. And it's a pretty darn good representation of what that matrix looks like. However, our result is not a matrix. Our result is a 1D array. So you use this little trick here. I'm not going to explain it. You just essentially take a 1D array and make it a 2D array with just essentially one column. So convert it into a matrix instead of just a vector. Convert it into a matrix with one column. Okay, it's just one column matrix. Okay, and what happens is you get this, right? That looks pretty cool. Like, oh yeah, look at the heat transfer in the rod. It's being heated in the middle and it's cooling off around the edges. So numpy.reshape, you take your 1D result and convert it to a matrix of size 1 by n. So it's still a column vector, but we asked Python to interpret it as a 2D array. But the 2D array is size 1 by n. Yeah. Kelvin. The x-at, okay, no, yes, great question. Thank you so much. So this is not the location on the rod. This is the index of the point. We have 100 points. So great catch. Thank you. Okay. All right, so let's get back to the lecture. We want to finish off today, I'm hoping. Now, I want you to recall this figure that I showed you a while ago. And we kind of dabbled a little bit with an increasing number of equations. These direct solvers become very expensive. And in a homework from the past, my students had to produce this plot, comparing standard solvers, okay, as the number of points or the number of equations increases. And then I showed you this plot last lecture actually, lecture before that. And I promised you that I will show you a method that scales with this black line, much cheaper method. The point is these direct solvers are very expensive, all right? Luckily, only for tridiagonal systems, okay? Only for tridiagonal systems where the matrix is mostly zeros, is all zeros, except for the three main diagonals. Main diagonal, first upper, and first lower. Luckily, there is a method that is very efficient and very fast, and it is a direct solver. Okay? It is a direct solver. Let me make sure.
What is a solver that's not a direct solver? This direct
So so as we discussed in one of the previous slides, indirect solvers, also called iterative solvers, are not exact. They approximate the solution. We're not going to study them this semester, but they are going to be in additional material that I will explain in a minute by the end of this chapter, okay? We're not going to cover those in this year. Okay, let me just double check that I have the recording going on. Okay. This method is called the tridiagonal matrix algorithm. It's not a very ingenious name, right? It's a tridiagonal matrix. It's a method to solve a tridiagonal matrix in a very efficient way. The method is called TDMA, also referred to as the Thomas algorithm. So we will use that name interchangeably. TDMA or Thomas or tridiagonal matrix algorithm. It is a special direct solver. Pay attention to what I'm saying. It is a special direct solver only for tridiagonal matrices. A direct solver is an exact solver. Okay? It solves the system of equations exactly. Like numpy.linalgebra.solve, and using numpy.linalgebra.inverse. Those are direct solvers. They solve the system of equations exactly. Okay. Like I said, it's also known the Thomas algorithm, and the TDMA applies to tridiagonal matrices. We know that. And those matrices arise from the solution of boundary value problems, heat and mass transfer, but mostly 1D problems. Okay? It's rare to have a tridiagonal matrix in 2D and 3D. In 2D and 3D, you get pentadiagonal and higher diagonal matrices. And there are no straightforward algorithms for those, unfortunately. Okay? The idea, though, is that the cool thing about this method is you do not need to store the entire matrix. So that's one of the primary benefits. We don't need to store all of those zeros that we don't need. We only need to store the main diagonal, the first upper, and the first lower. So our storage requirements go from n squared to 3n minus 2, the number of non-zero entries in the matrix. Okay? So that's a big benefit. From here onwards, we're going to use this nomenclature for tridiagonal matrices. The entries on the main diagonal, we're going to call them D's, because they're the main diagonal. The first upper, we're going to call them U, and the first lower, we're going to call them L. Okay? And we're going to start indexing from 1 to n for simplicity. So D5 is the 5th entry along the main diagonal. Okay? Dn is the nth entry along the main diagonal. All right? Every year, I used to present the TDMA, give the recipe, and many questioned, like, how did you come up with this recipe? So this year, I decided to actually derive it with you, but that means you will be responsible for also reproducing that derivation, all right? So that's the price that's paid by. But it's really easy. It's really straightforward, okay? So the idea of the TDMA is, first, it converts the tridiagonal matrix into an upper triangular one. Why upper triangular? Because an upper triangular matrix can be solved very quickly with backward substitution. There are flavors of the algorithm that can convert the matrix into a lower triangular matrix. There's just the same, give you the same result, but a different indexing and things. Okay, so here's an upper triangular matrix, right? So all the diagonals above the main diagonal are non-zero. Okay, and all the elements under the main diagonal are 0. So that's an upper triangular matrix. For this system, you can solve it by backward substitution. What that means, we start by solving the last equation, which is 5x3 equal 10. That's the last equation. You get x3. Then you go to the next one from the bottom. That's 5x1 plus 2x2 equals 3, plus 2x3 equals 3. But you know x3, right? You just solve for it. So you solve for x2. Now you have x2, x3. You substitute them into the first equation, and you solve for x1. So if this matrix is of size 1000 and it's an upper triangular, you start with the last entry and build the solution backwards. That's called backward substitution. Okay? So the TDMA proceeds by first converting this tridiagonal matrix into an upper triangular, I called it upper diagonal, upper triangular matrix. Let me fix that. Okay, into an upper triangular matrix, right? Because when you look at it, like, oh man, we're just so close to having this an upper triangular or a lower triangular matrix. Turns out this is entirely possible. So we start by equation 1. This is only an example of a 4 by 4 matrix, but the same thing applies to an n by n matrix. First equation remains untouched. d1x1 plus u1x2 equal b1. We don't touch that. We leave it as it is. Next, we go after equation 2. If we want to convert this into an upper triangular, we need to knock out L1. L1 needs to be 0, right? So that this becomes an upper triangular, starts becoming an upper triangular. So what we're going to do, we're going to take equation 2 and combine it with equation 1. In a system of equations, you can combine these equations in any way you like, as long as you're combining them linearly, and your system will still be the same. It will not change the answer. Okay? That's one of the rules of systems of equations. You can take 2 times equation 1 minus 3 times equation 2 and change equation 2, and you'll still be fine. Okay? These are linear combinations of the equations, and they will not change your answer. So that's what we're doing here. We're going to take equation 2 and combine it with equation 1. So if I write equation 2, it's L1x1 plus D2x2 plus U2x3, agreed? L1x1 plus D2x2 plus U2x3 equals B2. Under it, I'm going to write equation 1, which is D1x1 plus U1x2 equal B1. My goal is to knock out x1 from equation 2. Remember, I'm converting equation 2. And I want to get rid of L1. That means I want to get rid of x1. So if from equation 2, which is the first on the line, if I subtract L1 over D1 times equation 1, what happens here? L1 over D1 times D1 x1 becomes L1 x1. I subtract it from the one above it, becomes 0. Right? So I've modified equation 2 by subtracting from it L1 D1 times equation 1. And that gives me a new equation 2. It changes the coefficient for x2, changes the right-hand side, but I don't have x1 anymore. So I got rid of L1. So that's your new equation 2. Now, what you do, you call this one D2 prime. That's your new diagonal entry for equation 2. And this is your new right-hand side for equation 2. And this is what you get. Equation 1 was untouched. Equation 2, we changed it by combining it with equation 1, but then we were able to eliminate L1, but that meant we had to change D2 and B2. But that's fine, because now we're starting to see how we're going to build an upper triangular matrix. Now we do the same thing. We go at equation 3. I want to get rid of L2. In other words, I want to get rid of x2 in that equation. So I'm going to take equation 3, which is L2 x2 plus D3 x3 plus U3 x4 equal B3. And I'm going to write the new equation 2 under it. See the D2 prime and B2 prime. And look at that. I have x2 in common. So if I multiply equation 2 by L2 over D2 prime and subtract from equation 3, then I can eliminate x2. So I get 0x2, which eliminates L2, and a new coefficient on the main diagonal for x3, and a new coefficient and a new right-hand side. Again, I'll call this D3 prime, and I'll call that other one B3 prime, and now that's what's happening to equation 3. See, we went to equation 2, we eliminated x1. We went to equation 3, eliminated x2. The last one is the same thing. We're almost getting to an upper triangular. But we had to change the main diagonal coefficients. That's fine. That's what you do if you had two equations and two unknowns and you're doing substitutions. You solve for one, you replace it, etc. That's exactly what you would be doing. Except that this is so straightforward for tridiagonal matrices. We do the same thing for equation 4. Also, from equation 4, we subtract L3 over D3 times equation 3. And the same thing happens, magic happens, and ta-da, you get a upper triangular matrix. We started with D1, D2, D3, D4, L1, L2. We no longer have the lower diagonals. Yes, Miles?
So we multiply the second part equation, the D3x3 by the L3 over D3 prime. How can it multiply just into the D3x3 and not?
It multiplies the whole thing.
Oh, I'm dumb. Sorry. I didn't see
Sorry.
that.
I forgot the parentheses, but it does multiply the entire equation, okay?
Oh.
It multiplies the entire equation.
Basically, it's the same thing as multiplying that row by a constant.
Yep, exactly. So now we've converted our tridiagonal system into an upper triangular system, and then we just proceed by backward substitution. We solve for x4 equal b prime 4 over d prime 4, then we go to x3, go to x2, etc. Now the good thing is that when you want to do this in Python, you don't have to create a new matrix and call them D2 prime, D3 prime, D4 prime, etc. You just do it on the spot. Because as you are updating your values for the D values, they're automatically updated in the spot. You say my new D is equal my old D plus something or minus something. This is what the algorithm looks like. You start from 2, remember, equation 1 was untouched. So we start with equation 2 for I going from 2 to n. We start with equation 2. We take d2. The new d2, or d2 prime, is equal to d2 minus u minus 1, u I minus 1, l minus 1 over di minus 1. Exactly what we did in the formulas in the slides before. Same thing for b. So you create this new matrix with the d2 prime, with the d primes and the b primes. And then you proceed by backward substitution. You start with the last entry, xn, and you build the solution backwards. Okay? That's it. That's the tridiagonal matrix algorithm. Okay? Yes?
How can you prove it's faster?
You'll see. It is, so we observe that it's faster, but there are ways to look at the order of operations that are needed when solving a full system of equations, even if it has a lot of zeros in it. If you count the number of operations in Gauss-Seidel, for example, which is what the standard solve method would be doing, and compare the number of operations to this, this is orders of magnitude cheaper. Because what you're doing here is you can count. You have one subtraction, one multiplication, one division, and another subtraction, another multiplication, another division. So you have 1, 2, 3, 4, 5, 6 operations, and then 7, 8, 9 operations, okay, times n. So it's an order n algorithm, we call it. With Gauss-Seidel, you have probably an order n squared or n log n, okay? So, but we're going to observe. We're not going to dig into that kind of analysis. We're just going to observe that it's actually faster, okay, by timing it, all right? Great question. Okay, so now you're going to do this by hand. You're going to take the following system of equations and solve it with the Thomas algorithm. Work as groups. My advice to you is to first convert it into a tridiagonal matrix. Write it in a tridiagonal matrix form. Write your di's and bi's and upper diagonal and lower diagonal. Right? Remember, the TDMA only needs the 3 main diagonals and the right-hand side. This is an exam problem. Okay, this is actually from an exam problem. No. That's a rumor. There's no exam next week, guys. So write the equations. My recommendation is that you write it in matrix form. You identify the main diagonal, the first upper, the first lower diagonal, okay, the right-hand side, and build the solution. Okay. In the interest of time, I'll show you my solution. Okay. Okay, so the first step, I would write this in matrix form. And it's already in tridiagonal form. It might not be given to you in tridiagonal form, so you might want to rearrange the equations so that it looks as a tridiagonal system. Then we need the 3 main diagonals. So that's what I would write first. I would write L as a vector, D as a vector, U as a vector. So that, oh, what is L2? Ah, this is L2. This is L3. This is D2, D4, okay? So you don't have to worry about negotiating that in the matrix, okay? And then you write the right-hand side vector, or you can even write them manually, B0 or B1, B2, B3, B4, okay? Next step, you have those. Next, you implement the TDMA. Step 1 is converting the main diagonals, converting the matrix into an upper triangular one. I know you could do it by just by looking at the matrix, but I don't want you to do it that way because you need to learn this process so that you can do this in Python. Python is not going to know how to make it an upper triangular matrix by visually looking at it and adjusting the coefficients. It implements the formula that I gave you, okay? So step 1 is converting di's and the bi's, or doing the D2, the D prime and the B prime. And we're going to start with equation 2 all the way to the end. So that loop goes from I equal 2 to I equal n. We start with I equal 2. That's equal to D2 minus U1 L1 over D1. Okay, you got L1, you got U1, and you got D1 up there. You just plug them in, and you get 7 over 2, whatever. And then B2 is B2 minus B1 L1 over D1. Again, you get the same thing, and you get a 4. Yes?
So that D2, that's the main diagonal, right? What do you do with the lower and upper two?
You don't worry about those, because that's automatically converting it to an upper diagonal.
So you just get rid of that?
You're not working with the matrix anymore.
Well, no, we still have the L and U.
But they don't matter in the solution process, right? Because the new, now, in this step, Miles, we converted the second equation. There's no more L1 in the second equation anymore. It doesn't matter anymore, because we converted now the second equation into an upper triangular, okay? Now we're going to continue with the third equation, the fourth equation, and then L is not going to matter anymore, okay? Now you go to equation 3. The new D3 is equal to the old D3 minus U2 L2 over D2. Which D2 you choose? You choose the one that you just computed, all right? Because in the mathematical derivation we did, that was D2 prime, okay? So you choose the D2 that you just computed. You see 7 over 2. Same thing with B3. It's B3 minus B2 L2 over D2, that most recent D2. And then you go to the last equation, okay? Dot, dot, dot. Now, at this stage, the system has been converted to an upper triangular matrix. What are the entries in the upper triangular? They are D1, which is the standard D1 that you have, and the new D2, the new D3, and the new D4. There's no more L anymore. The upper diagonal is still the same, is untouched, and then the right-hand side is this new B, okay? Now, step 2 is the backward substitution. We're going to start with the last equation. Remember, in the upper triangular matrix, we start at the end. The last equation can be solved directly, because it's going to be dnxn equal bn, right? So you solve directly for xn. And then we proceed backwards. So we're going to start with x4, which is equal to b4 over d4, whatever you got from up there, and that gives you 4. And then x3 is going to be b3 minus u3 x4 over d3. You have x4, you plug it in here, and then you solve for x3. Yes?
I'm a little bit confused on the B3 step and step 1. Where did you get the
So that is going to be L. Okay, hold on. You're right. So B3, I might have made a mistake here. Okay, B3 is 9 minus B2, which is 2, times L2, which is 4. So I do have a typo over here.
Isn't the new B2
It should be the new B2. Yeah, so I do have a typo over here. I do have a typo over here. Yeah, this is, okay, however, it's not going to affect the solution, but you're right. Good catch. Good catch. Good catch. Thank you. I'll fix that, okay?
Wouldn't it still be 4, though, not -2? And then that would change your B3 answer?
It will change the B3, yeah. So you would have, okay, so you would have the old B3, which is 9, right? Minus the new B2, which is 4, okay? Times L2, which is 4, so you'd have minus 16 over 7 over 2, right? So you'd have whatever, 9 minus 16 over 7 over 2, whatever that is, okay? Good catch. Thank you. Okay? Now with the backward substitution, I don't know, I have this probably screwed up over here, but I might have the right answer. Does anyone have a calculator? Did you do it? Did you do it right, Abigail? Okay, and B2 is B2 is equal to 2 minus, okay, B1 is minus 4 times L1 times 1 over D1, which is 2, okay? So we got B2 right at least. So do 9 minus 16 over 31 over 7, okay? So I got the right answer at least, but the mistake It's just that one, okay? Well, thank you for catching that. I will fix that, okay? You see what happened is I wanted the solution to be 1, 2, 3, 4, and I changed it from an older exercise, but I didn't fix this one. But anyway, you go through x3, and then x2, and then x1. Why are we doing this? We're solving the system of equations. That's what this algorithm is doing. This is not linear algebra, guys. This is numerical methods. This is a technique, a technology of sorts that allows you to solve a linear system of equations, a tridiagonal system of equations. Okay? So that's the objective, is to finding those x's. Now I ask you, what types of errors are present here?
None.
Okay, we got none. No errors.
Well, if you did it in a computer, obviously there would be errors.
Okay, we're doing it on a computer.
No, if you did it on
Of course we're not doing linear algebra, we're not doing math here. What kinds of errors are existent here? That's the last time you asked me that question. Okay, so what do you say now that we're solving it? Round off and truncation?
round off.
Round off or
Just
okay.
round off.
Just round off, okay. Round off. Pardon me?
I'll say round off with Mike. I could give you some round off.
Okay. Who else? Let's think about it. Is there any truncation going on here? First, is there round off error? This is on a computer, not exact math like 32 over 7 or whatever. On a computer, is that going to be round off? Yes, yes, always, of course, yes. Anytime you're multiplying, adding, dividing, we're going to have round off. So we do have round off, 100%. Do we have a truncation error? Okay. Yeah, I love you guys. Yeah, you got it. There's no truncation error. We're not doing truncate anything. For all we know, you have a system of equations. That's it. You got a system of, you didn't truncate anything. You didn't change it. You have a system. That's it. You didn't make any approximations on that system. You didn't truncate it in any way. Okay, you didn't take an exact formula and approximate it, truncating it with the Taylor's. No, nothing. Now, how did we obtain that system? Maybe there was a truncation error getting to that system, but for all you know, you don't know that. So in the heat transfer problem, we have a truncation error when we get to the discrete equation, but once you formulate the system of equations, that's a system of equations. In solving that system, you are only incurring round-off errors. That's it. Okay? Anytime you're computing two numbers on a computer, adding them, multiplying, dividing, you have round-off.
Even for using integers,
If you're using integer arithmetic, there's no round-off.
if we use integers on a computer,
Well, you have floating points here, right? So 31 over 7. If you make it an integer, it's going to return, it's not going to work. It's not going to give you the right answer, okay? It's going to give you an integer answer, but that's worse than round off, right? It's the wrong solution. It's the wrong answer. Okay, so let's Pythonify this. Okay, this used to be a homework assignment 4 years ago, but I don't want to grade that homework assignment anymore. So I'm giving you the formula from now on. I'm giving you the subroutine, okay? But now your burden, you're held to a higher standard because you have to know how to use this, right? So previously the homework was write the Thomas algorithm. Now use the Thomas algorithm to do fun things with it, okay? So this, you're going to use this with your upcoming homework 4, okay? You can copy it, reuse it. I give you permission to reuse it. If we see it in our codes, in your codes, you have my permission to use it. That's not copying or, not right. This is, you have permission to use this. You don't have to change the variables or anything. Keep them as is, okay? So this is on the slides, but you can copy it from tomas.py in your homework folder. Or you can also do it in Python. So let's download this linsolve activity 3. Use TDMA with gaps, okay, to solve this system. So let me explain to you first. Let me explain to you first what the Thomas subroutine takes. The way I think about programming when I want to create a subroutine is what inputs do I need and what do I need to return. Okay, at a minimum, the Thomas algorithm needs the 3 main diagonals and the right-hand side. You could say, well, Professor Saad, I want to pass the matrix. No, that would be foolish, because if you want to pass the matrix, you're passing a full-size n by n matrix, which consumes a lot of memory. However, when you're passing the 3 diagonals, you're passing 3n minus 2 memory size, okay? So no, do pass the diagonals, main, lower, and upper, and the right-hand side. That's all the Thomas algorithm needs to figure out what it needs to do. And what does it return? It returns the solution to the system of equations, okay? So it brings in L, D, U, and B, so that descriptive lower, main diagonal upper, and right-hand side, and it returns a solution vector, okay? So you're going to use that to solve this system of equations. Let's grab this notebook, open it.